Okay. So my PhD thesis is all about scheduling arrivals in to queuing systems. So today I plan to talk about one of my projects. The title is Scheduling Customers into a Stochastic Server System in the Presence of Random Customers. So scheduling is a well-known, efficient approach of controlling arrivals in queuing systems. If we look into the literature, there are a lot of discussions about scheduling arrivals in queuing systems, especially considering stochastic service times. Further, there are discussions about uncertainties such as early arrivals, delayed arrivals, cancellations, no-shows, and random arrivals. Although there are a lot of discussions about these uncertainties, there are only a few works have addressed have derived mathematical models to schedule customers in the presence of these uncertainties. So that's why we choose this topic. Some researchers discuss the effect of random customers for a system with the scheduled customers. For example, Kailry and Verel mentioned that the random customers are not considered in most studies, although random customers appear in the system. And Fimes, Kuhl, and Neen presented the effect of emergency arrivals on scheduled patients' waiting time. So this scheduled patients' waiting time is highly affected by emergency arrivals because emergency arrivals gets priority over these scheduled patients. So if we dig into the literature on scheduling customers in front of, in the presence of random customers, there are two remarkable works. The first one is done by Ramani and Haidari. They developed a dynamic scheduling approach to systems that accept both scheduled and random jobs. So first I will tell you what is the difference between dynamic scheduling and static scheduling. So dynamic scheduling is also known as online scheduling. So in dynamic scheduling, the scheduler decides the arrival time of the I plus first scheduled customer when the ith arrival actually happens. So the scheduler considers all the uncertainties that occur until the ith customer's arrival instance, and then decide what would be the optimal arrival time for the I plus first scheduled customer. So on the other hand, in static scheduling, the schedule is decided before commencing the system. So for example, if we consider a medical clinic, the system manager knows what would be the arrival times of the patients at the beginning of the day. Static scheduling is also known as offline scheduling. So here in dynamic scheduling, we have more information than static scheduling. So there are comparisons about dynamic scheduling and static scheduling in the literature. Many researchers have shown that dynamic scheduling is efficient than static scheduling. Also, static scheduling is highly computationally expensive than dynamic scheduling. In this research, we consider systems like a medical clinic or a barbershop, which deals with people. So in that sense, dynamic scheduling is not that reliable because the arrival time of a customer is decided in a short time. So therefore, we focus on static scheduling in this discussion. So the other work is done by Wong, Liu, and Wan. They developed a static scheduling approach where the decision variables are the number of customers to be scheduled in equally divided time intervals of the day for systems that accept scheduled and random customers. So in this project, they consider deterministic service times and assume that a service time is one time unit, and their aim is to decide the optimal number of customers to be scheduled at the beginning of each interval. And their objectives are to minimize the total expected customer waiting cost, to minimize the total expected server idle cost, and to minimize the total expected overtime cost. So now let's have a look at our model. So here we consider a system that accepts both scheduled customers and random customers, where the system has only one server and it starts with the first scheduled customer's arrival. The random arrivals occur according to a Poisson process with the rate lambda until the last scheduled customer arrives. Random customers are no longer accepted once the last scheduled customer has arrived, but all customers still in the system are served. So at the arrival of the last scheduled customer, the system stops accepting further arrivals, but continue to serve those customers who are in the system at the last scheduled customer's arrival until they all get served. The service times are exponentially distributed with mean 1 or mu. We give non-preemptive priority to scheduled customers. We will discuss what this non-preemptive priority means later. The maximum waiting room capacity for random customers is finite, which we denoted by capital M. So here we do not consider any waiting room constraint for scheduled customers, because we need to schedule some fixed number of customers. So we know that there is a finite number of scheduled customers for the service period. Also, we assume that scheduled customers are punctual. So what does non-preemptive priority mean? So here we give priority to scheduled customers over random customers, but if a random customer starts service, even when a scheduled customer arrives, he can't disturb the service of that random customer. So in this first case, when this ith scheduled customer arrives, he sees an empty system, and he can directly start service without waiting. So in second and third cases, when this ith scheduled customer arrives, he sees some random customers in the queue. And in second case, there's a scheduled customer in the server. And in the third case, there's a random customer in the server. So if we think of this third case, even though this scheduled customer has priority over this random customer, this customer cannot disturb the random customer's service. So this ith customer stands in front of the queue, and these two random customers has to move back one position. Again, in fourth and fifth cases, when the ith scheduled customer arrives, there are a bunch of random customers and a bunch of scheduled customers in the queue. And in fourth case, there's a scheduled customer, and fifth case, there's a random customer. So this ith scheduled customer's position in the queue is not affected by the type of the customer in the server. So this scheduled customer joins the end of this QS, and again these random customers has to move back one position. So our objective is to determine the optimal schedule for n customers, so that the total expected cost of customers waiting and that of the server being idle is minimized, while the system's expected revenue is maximized. So in the thesis, there's a long discussion about different objectives. So, but for this discussion, we fix that our objective is going to be the combination of these three objectives. We denote our decision variables by vector x, where x is equal to x1, x2 up to xn minus 1. Xi here is the inter-arrival time between the ith and I plus first scheduled customers' arrival times, and Ti is the arrival time of the ith scheduled customer, so that Xi is equal to Ti plus 1 minus Ti. So this problem is a multivariable, multi-objective optimization problem. We define the system state at the ith scheduled customer's arrival as Vi, which is equal to Ki Mi Li for I goes from 1 to capital N, where Ki is the number of scheduled customers in the system at the ith scheduled customer's arrival. Ki range from 1 to I, because we consider the system size is a right continuous process. So when the ith scheduled customer arrives at the system, the total number of scheduled customers is including him. So Mi is the number of random customers in the queue at the ith scheduled customer's arrival. Mi range from 0 to capital M. So at any time of the service period, the maximum number of random customers in the queue should be less than or equals to capital M. And Li is the number of random customers in service at the ith scheduled customer's arrival. Li equals 1 if a random customer is in the service at the ith scheduled customer's arrival and 0 otherwise. The system state at the first scheduled customer's arrival is V1, which is equal to 100 with probability 1, because we assume that at the beginning, at the commencement of the system, there are no random customers. So now we need to write down our objective function. Let WSI is the expected waiting time of the ith scheduled customer. So at the arrival of the ith scheduled customer, we can directly write down what would be his expected waiting time by looking at the system state at that time. But for random customers, so those arrivals are random, even though if we know the arrival time of this random customer, we cannot write down that specific random customer's expected waiting time, because these random customers expected waiting time is affected by the future scheduled customers' arrivals. So we consider an interval between two consecutive scheduled customers and try to find out what would be the increment in total expected waiting time for random customers during that interval and sum up. And we do the same for expected revenue and expected serve idle time. So we define WRI as the increment in total expected waiting time for random customers who are present at some point during interval Ti plus 1. And ZR is the increment in expected revenue from random customers who arrive at the system at some point during interval Ti plus 1. Di is the increment in total expected serve idle time in the interval Ti plus 1. And Ci, Cs, and Cr are the costs of server being idle per unit time, cost of scheduled customer waiting per unit time, and the cost of random customer waiting per unit time respectively. And Qs is the revenue per scheduled customer, and Qr is the revenue per random customer. So this is our objective function, which we expect to minimize. So this first line gives us the total expected waiting cost for scheduled customers. And this second line in blue gives us the total expected waiting cost for random customers. And the third line is the total expected server idle cost. And the last line is the total expected revenue of the system, which is minus, because we need to maximize the total expected revenue. So before going to deriving these expected values, I would like to go through this theorem. Kleinrock showed that the arrival times are independent and uniformly distributed, conditional on the number of Poisson arrivals during a certain time interval. The theorem states that given that one event of a Poisson process has occurred by time t, that event is equally likely to have occurred anywhere in the interval 0 and t. So if there are Poisson random arrivals in an interval ti plus 1, they are distributed independently and uniformly during the interval of length xi. So the expected arrival time of a random customer is ti plus xi over 2. Therefore, the expected waiting time of a random customer is xi over 2. So the increment in the total expected waiting time for these R random customers during this interval is Rxi over 2. So as I mentioned earlier, we consider an interval between two consecutive scheduled customers to find out what are the expected costs and the expected revenue. So during this interval, there can be infinitely many possible events can happen. So we consider those events with non-negligible probability. So this event is the simplest one to understand. We don't have any service completions in this interval. So at ti, which is the ith scheduled customer's arrival time, we have the system state vi as ki mi li, and we do not serve any customers during this interval, and we assume that there will be ri random arrivals. So the system state changes as ki changes to ki plus 1, because these ki scheduled customers who were at the system at ti are still there, and one scheduled customer arrives. And mi changes to mi plus ri. We have mi random customers at ti, and there are ri arrivals during this interval, and it becomes mi plus ri. And li does not change because the customer who was being served at ti is still being served when this I plus first scheduled customer arrives. So this is the probability of that event. And so there are no departures and ri arrivals. The expected waiting time of the ith scheduled customer can be written as ki plus li minus 1 over mu, because there are ki plus li minus 1 customers in front of him. So this is the expected total expected service time. And WRI, which is the increment in total expected waiting time for random customers. So we have MI random customers at TI, and as no one gets served, these MI customers wait for the whole interval. So we add the MIXI, and these RI customers arrives at some stage during this interval. So their expected waiting time during this interval is RIXI over 2. So we add that. Also, these RI random customers brings RIQR revenue to the system. And as the system is busy throughout this interval, the expected server idle time is 0. So now let's consider a complicated case. So here we consider the situation where all the scheduled customers are served before the next scheduled customer arrives. So so if there is a random customer in the server when the ith scheduled customer arrives, then we need to we need to complete that service first and then start serving scheduled customers. So if you think of the situation where all the scheduled customers are served, we should serve KI plus LI customers. That can happen during any time during this interval. So for example, let's assume that the system serves KI plus LI customers at finish serving at TI1. So at this point, we don't have any scheduled customers, but we have MI plus RI random customers here. So at this stage, we need to think whether this MI plus RI1 is 0 or greater than 0. That means whether we have some random customers here or not. So we have two cases. For example, if we consider MI plus RI1 equals 0, where we do not have any customers at this stage, then we need to think whether there will be another arrival before this I plus first scheduled customer's arrival or not. So if there is no arrivals before this customer's arrival, then again this becomes easy to like write down those expected costs because the system is empty for this interval, and the system is idle for this interval, and we can write down what would be the probability of this event and what are the expected costs. But if there is going to be some arrival during this interval, so for example at TI2 less than TI plus 1, so at this point we need to think whether this the system can serve this customer, like finish serving this customer before the next scheduled customer's arrival or not. So likewise, there are like infinitely many possible events we can consider. So again, if there are some random customers at this point, then again we need to think whether we can finish serving all of these customers before next scheduled customer's arrival or not, and so on. So like if we consider these events, we can see that this residual time until this I plus first scheduled customer's arrival becomes small, so that the probability of an occurrence, like an arrival or a departure, becomes infinitesimal. So we ignore those negligible probabilities and only consider those probabilities with high probability, events with high probability. So for example, I would like to consider this case 2, where we have some random customers at this point, but we can't finish all of those services. So so at this point we have MI plus RI 1 random customers, and we only serve GI of them. So like we did previously, we can write down the state change here and the probability of this event. There are KI plus LI departures in this time length of tau naught, and RI1 arrivals. Also GI departures during this interval, and RI2 arrivals. So the increment in total expected waiting time for random customers can be written as here. So these MI customers wait for the whole interval TI1, and so we add MI tau naught, and RI1 customers arrive at some stage during this interval, so we add RI1 tau naught over 2. So at this stage we have MI plus RI1 customers, and we serve some GI of them, and one customer goes to the server. So we have MI plus RI1 minus GI minus 1 customers who wait for the whole interval. And again, following the previous theorem, we can write down the expected waiting time for RI2 customers and GI customers. So now, as I mentioned earlier, we assume a finite waiting room capacity for random customers. So if you think of a physical system, then if there is a finite waiting room capacity, usually the system chooses the customers according to their arrival. For example, if in an interval, like if we assume that the finite waiting room capacity is like 4, and if there are like 10 arrivals during an interval, the system choose the first 4 customers usually, which is too complicated to derive mathematically. So for this discussion, we assume that if there are more than the capacity, the system chooses customers randomly. And in the thesis, we extend this to this with relaxing this assumption. So for now, we stick into this assumption because it makes it easier to derive these expressions mathematically. So this lemma is about how to find out the increment in the total waiting cost for random customers. If we allow at most m random customers to get into the system, then the expected increment in the total waiting cost in an interval ti plus 1 of length xi is given by this expression. So what we do here is, so we consider 2 cases. If the number of arrivals during this interval is less than the capacity, less than or equal to the capacity, then we accept all of them. And if the number of arrivals is greater than the capacity, then we only accept m, like m of them, and we can simplify this expression as here. So if I go back here, so if we assume that we have a finite waiting room capacity of capital M, so at this stage we have mi random customers, and the capacity at this point is capital M minus mi, and we assume that this so that this Ri1 cannot exceed capital M minus mi. So this is, as I mentioned earlier, this is a multivariable optimization problem, and if we need to schedule capital N customers, we have n minus 1 variables. So it is quite complicated to write down the whole objective function at once. So we use a recursive form to generate the cost function. We define Ri, Ki, Mi, Li as the expected cost of the system from the ith scheduled arrival to the end of the server open time. If we have Ki scheduled customers in the system, Mi random customers in the queue, and Li random customers in the server, for I goes from 1 to capital N. So, so this recursive form of the cost function has a lot of convolutions because we consider like several cases during an interval. So it is not easy to solve in that form. Therefore, we convert it into Laplace domain, and we define the Laplace transforms of the cost function as Ri star. So let's have a look at the Laplace transforms. So this is the Laplace transforms of our recursive cost function, and we use backward recursion to write down the cost function because at the last scheduled customer's arrival, we stop accepting further arrivals, so that if we know the system state at that time, we can write down what would be the expected cost of the system. Also, we know that the system state at the beginning of the server is 100 with probability 1. So you can see that this is a quite long equation for the Laplace transforms as well. So this is our boundary condition. So this Rn is the cost of the system since the nth scheduled customer's arrival until the server conclusion, and here is the Laplace transforms of the boundary condition. So how we solve this problem? So here we use a black box technique. For example, if we consider scheduling 5 customers where we have 4 decision variables. First, we assume that our initial guess is x1. So if we feed x1 into this black box, then it gives us the objective function value. So I'm not going to discuss about what happens inside this black box in detail, but if I summarize, what we do is we use single variable numerical inversion of Laplace transform in some dynamic way to generate these objective function values, as there are no theories developed to invert multivariable Laplace transforms in any way. So as this black box gives us objective function values, we use an evolutionary algorithm to approximate the optimal solution. So here we use covariance matrix adaptation evolutionary strategy algorithm, CMAES. So why we choose this algorithm is because we compared CMAES and simulated aniline for this for our problem. So when the dimension is low, like n equals 2 or n equals 3, where we have 1 variable or 2 variable, we can solve this analytically. Therefore, we have results analytically for n equals 2 and n equals 3, and we use CMAES and simulated aniline to approximate the solution, and compare these solutions with analytical solution. So CMAES is faster and more accurate for this specific problem. Therefore, we choose that. So as I mentioned earlier, we have analytical results for n equals 2 and n equals 3. So this is a comparison between the black box approximation and the analytical solution for n equals 2 and the waiting room capacity 5. So after like 15 iterations, we got the exact solution. So we have confidence about like using this black box approximation. Also, when we increase the dimension, we can't compare with the analytical solution. So what we did is we choose multiple start points, and the final solution is pretty close, like to the 3rd decimal point. So we have confidence about this black box approximation. So before going to our results, I would like to go through Stein and Court results. So what Stein and Court did is they considered stochastic server system, where the service times are exponentially distributed, and assume that there are only scheduled customers in the system, and find out what would be the optimal schedule. So here gamma is this ratio here, CS over CS plus CR, where CS and CR are the unit costs of server being idle and customer waiting respectively. So why I'm showing this result to you is because I need to compare this result with our results. So these are some results that we generated for different number of customers to be scheduled. So we can see a same pattern. And this red line is for scheduling 10 customers to a system where the server is stochastic, service times are exponentially distributed, and the system accepts both scheduled and random customers. So in stain and court results, it's like it increases and flatten at the middle, and then it drops. But here in our model, in this problem, this interarrival times are increasing. We cannot see a dome shape here. So why this is increasing is because we have random customers and we need to maximize the revenue. At the same time, we need to minimize the customer waiting cost. So we start here, and like during this interval, there are some random customers arrives, and they bring some revenue. And like at the arrival of the second scheduled customer, there are some random customers. There can be some random customers in the system. So like in order to minimize their waiting, the interarrival times increases. And at the same time, there are other random customers arrives at the system. So why there's a sudden drop here? Because at the last scheduled customers arrival, the system stops accepting further customers, and there are no scheduled customers, no random customers. So if there are some random customers at that point, their waiting time is only affected by scheduled customers. So it allows some random customers to get in the system to bring some revenue, and minimizes the waiting cost. So so at the beginning of this discussion, I mentioned a paper which mentioned that random customers are not considered in scheduling in most of the cases, even though they appear in the system. So we compared these models with our model. So this related cost is generated by, so first we considered a system which accepts random customers but generated a schedule without considering them, and for that specific optimal interarrival time, we found what would be the related cost of the system. And this optimal cost SR is when we consider both scheduled and random customers in deciding optimal interarrival time. So when we increase the number of customers to be scheduled, our proposing model is more efficient if we compared with the system with ignoring random customers. So these results are generated for m equals 2, where the waiting room capacity for random customers is equal to 2. So this minus value is because we need to maximize the revenue here as well. So if we change the waiting room capacity to 5, then it is even efficient. So we generated these results recently, and the other codes are still running on Spartan. It takes long time to run this code on Spartan. So yeah, so if we talk about future research directions, As I mentioned earlier, this static scheduling approach is computationally very expensive. And dynamic scheduling, on the other hand, is not reliable for systems dealing with people. So we suggest a mixed dynamic and static scheduling approach for scheduling customers into these type of systems. Another interesting direction would be scheduling customers into stochastic service system in the presence of strategic customers. So in this work, the system manager decides which customer gets in the system and which customers do not. But in this suggesting work, this strategic customers decides whether they join or not, looking at some information they get. Another interesting work would be scheduling patients into stochastic service system in the presence of emergency patients. So in our work, we gave priority to scheduled customers, but if there are emergency patients in front of scheduled patients, then emergency patients get priority. So this would be an interesting direction. So this is the end of my talk, and I should thank the University of Melbourne for financial support through the Melbourne Research Scholarship, and ASIMS for supporting, financially supporting for attending conferences, and all the support to improve my soft skills and research skills, and OPTIMA for giving me opportunities to improve my soft and research skills. And thank you everyone for listening to me.